Welcome to the deep dive. This is where we take some really dense source material, the research papers, architectural diagrams, all that technical stuff, we break it down, and basically hand you the synthesized knowledge, the goal, to help you get up to speed fast.
And today, we're tackling something truly fundamental. We're diving deep into, well, the engine of modern computing, database systems.
Right.
The source material we've gone through is incredibly rich. I mean, it traces the history from 1970s mathematical theory right up to the absolute cutting edge, even quantum computing concepts.
Wow. Okay.
And look, this isn't just about spreadsheets or simple lists. We're talking about persistent, secure, scalable data management, the heavy lifting stuff.
So our mission here really is to give you the ultimate shortcut. We want to take you from maybe a basic idea of storing data to really grasping the sophisticated architecture that underpins pretty much everything digital.
Everything. E-commerce transactions, cloud services, social media, it's all built on this.
You're about to understand why we just sort of implicitly trust these systems to work.
And it's so important to establish right off the bat why they're foundational. The absolute core concept is data persistence.
Persistence.
Yeah.
Meaning it sticks around.
Exactly. Databases don't just hold data temporarily. They guarantee that the information you commit, the stuff you save, will survive. It'll survive a process crash, a hardware failure, even a sudden power outage.
Okay, and how do they make that guarantee? That sounds like a big promise.
It is a big promise. It's achieved through, well, durable storage mechanisms, think. Hard drives, SSDs, combined with some very sophisticated logging protocols, which we'll definitely get into.
Right.
It's like this silent contract we all have with the digital world. You save your data, it'll be there tomorrow. That's the expectation.
And that guarantee makes the evolution from the early days really fascinating, doesn't it? Because it wasn't always like this.
Oh, absolutely not. We moved from these very early structures that were basically just application-specific flat files. Think simple text files, maybe.
Where keeping things consistent was that messy.
Completely the programmer's problem. If you had the same piece of data in two files, you had to make sure they were updated together. It was a maintenance nightmare.
Okay.
Then we shifted to these centralized systems that could actually reason about things like data integrity, handling multiple users at once, concurrency, and security.
Right, taking the burden off the individual programmer for those core things.
Precisely. And COD's breakthrough, which we need to talk about, fundamentally shifted that data maintenance. It went from being this chaotic, custom coding job for every application to being an automated, mathematically rigorous function of the database system itself. It was a huge leap.
Okay, let's unpack this whole journey then. We should probably start with that relational revolution you mentioned with COD.
Definitely. That's the logical starting point.
Then maybe we can dive into the engine room, how the data actually gets stored, indexed, how the system makes it fast.
The physical side, yeah. Buffer pools, B trees, all that good stuff.
Then we have to tackle the really complex parts. Transactions, making sure things stay correct when multiple people are doing things at once, and what happens when you spread databases across multiple machines. Distributed systems.
Ah, yes. Get ready for the CAP theorem. That's always a fun one.
Always. And then we can wrap up by looking at the modern landscape, right? NoSQL, serverless stuff, maybe even peek at the future.
Exactly. The wild frontiers, as you put it, NoSQL, NewSQL, even quantum database concepts. It's a huge field. Hashtag, tag, one, the relational revolution and core responsibilities.
Okay, so that relational revolution, to really get why it was such a big deal, we probably need to touch on what came before 1970.
Yeah, you really do. Before COD, the data management world was, well, it was dominated by systems like IBM's IMS, that's a hierarchical information management system, and the network model, which was standardized by a group called Codicil.
Hierarchical and network. What did that actually mean in practice? How did they work?
Well, think of IMS like a strict family tree. Data was organized in parent-child relationships, very rigid. The network model was a bit more flexible, like allowing a child record to have multiple parents, creating a graph structure.
Okay.
But both were efficient for the specific tasks they were designed for. The problem was they imposed these incredibly rigid structural constraints. Meaning the way data was related, the connections between records, were often defined by physical pointers stored on disk. Navigating the data meant following these predefined paths.
So if you wanted to ask a new question, one the system wasn't originally designed for.
You were often in trouble. You might literally have to rewrite parts of your application logic because your query was inherently tied to that specific physical storage path. There was very little flexibility.
Right, the application knew how the data was stored, not just what data it needed.
Exactly. That coupling was the problem. And that's where the genius of E.F. Codd's 1970 paper comes in. It was this radical separation of concerns.
Okay, what did he separate?
He proposed separating the logical representation of the data, how users and programmers perceive it, as simple, clean, two-dimensional tables.
Like a spreadsheet view.
Sort of, yeah. Separating that view from the physical storage mechanisms, how the data is actually laid out on disk, the sectors, the pointers, the indexes.
Ah, okay. So the user doesn't need to know about the messy details underneath.
Precisely. That abstraction, that separation was the revolutionary step. It meant the application programmer could suddenly focus purely on the logic of the data, the tables, the columns, the relationships between them, without worrying about disk sectors or pointer chains or any of that low-level stuff.
That's called data independence, right?
That's exactly it. Data independence, and it directly paved the way for declarative query languages.
Because you no longer had to tell the system how to get the data step by step, navigating those pointers.
Right. You could just declare what data you needed.
And that, of course, brings us to SQL, structured query language.
The undisputed king for decades. With SQL, you tell the system what data you want. Get me all customers in California with orders over $100. And the database's optimizer, which we'll talk about later, figures out the best, most efficient way to physically retrieve that data.
And this whole relational model, this SQL approach, led directly to the big enterprise systems we still hear about today.
Absolutely. The cornerstones: Oracle, IBM's DB2, Microsoft SQL Server, and then later, the really powerful open source giants like PostgreSQL and MySQL. They became foundational for businesses.
Why did they take over so completely? What was the big advantage?
They conquered the corporate world primarily because they prioritized consistency and reliability above almost everything else. The mathematical model, the ACD properties we'll get to, gave businesses trust.
But things change. The world didn't stay still.
No, it definitely didn't. As the 21st century rolled around, the internet just exploded in scale. Suddenly, you had applications needing to work across the entire globe, dealing with massive amounts of semi-structured data, user comments, social media posts, sensor readings.
Data that doesn't fit neatly into predefined rows and columns.
Exactly. And on top of that, users started demanding incredibly low latency, like microsecond response times for web pages.
Okay.
These pressures, global scale, messy data, low latency, really started pushing the limits of those traditional relational database management systems, the RDBMSs.
And that led to?
That friction really spawned the whole NoSQL movement, not only SQL, which prioritized scale and flexibility, sometimes at the cost of strict consistency, and also the NewSQL movement, which tried to kind of get the best of both worlds.
Okay, fascinating evolution. But before we get lost in NoSQL and NewSQL, let's go back to those core responsibilities of any database, especially the traditional ones. Beyond just storing rows and tables, what are the absolute non-negotiable things a database does for you?
Right, this is fundamental. The absolute bedrock responsibility, the thing that builds that trust we talked about, is transaction management. And this is usually guaranteed by what we call the ACD properties.
ACD, okay, that's an acronym, right?
It is. It stands for atomicity, consistency, isolation, and durability. The core idea is that complex operations, things that involve multiple steps, need to be treated as a single indivisible unit, a transaction.
Okay, give us that classic example everyone uses, the bank transfer.
Perfect example. Transferring money involves, let's say, at least 4 steps. 1, read the balance from account A. 2, write the new lower balance to account A. 3, read the balance from account B. 4, write the new higher balance to account B.
Right, multiple steps.
That entire sequence must be treated as one single atomic action, and ACD tells us how that action has to behave.
Okay, break down ACD for us.
ACD, it's all or nothing. If the power fails or there's any error between step 2 and step 3 in our transfer, the entire transaction is rolled back, it's undone, you don't end up with money disappearing from A but never arriving in B, no partial execution allowed.
Okay, crucial.
Consistency. This means the transaction takes the database from one valid state to another valid state, respecting all the defined rules. In the bank example, a consistency rule might be that the total amount of money across all accounts in the system must remain the same before and after the transfer. The transaction can't just invent or destroy money, it preserves the database's integrity constraints.
Got it.
Isolation. This is about concurrency. If you have thousands of users hitting the database at once, your transaction needs to be isolated from others. While your transfer is happening, those intermediate steps where A is debited but B isn't credited, yet no other concurrent transaction should be able to see that inconsistent state.
So other users only see the state before your transfer started or the state after it's successfully finished.
Exactly. They don't see the messy middle. It's like each transaction runs in its own little bubble, even though thousands might be running simultaneously.
And finally, D.
Durability. This is the persistence guarantee we started with. Once the database system tells you your transaction is complete, that it's committed, that change is permanent. It's recorded in durable storage, like on disk. Even if the entire system crashes 1 millisecond after confirming the commit, that completed transfer will survive the crash and be there when the system restarts.
Wow. Okay, ACD. Atomicity, consistency, isolation, durability. That really is the bedrock.
It absolutely is. It's a fundamental contract of reliability.
But achieving that isolation sounds incredibly tricky in practice. You said thousands of users hitting the system at once. How does the database actually manage that? That sounds like controlled chaos.
It is controlled chaos. That's concurrency control. It's the whole set of mechanisms the database uses to allow all that simultaneous access while still maintaining the illusion of isolation, making it seem like transactions are running one after another serially.
And why is that illusion so important? What happens if you don't have good concurrency control?
Oh, you get all sorts of nasty problems.
Yeah.
Things like dirty reads, where one transaction reads data that another transaction has written but hasn't committed yet. If that second transaction then rolls back, the first transaction has based its actions on data that technically never existed.
Yikes. That sounds like a recipe for disaster.
It can lead to cascading errors and completely corrupt data. So concurrency control mechanisms like locking or versioning, which we'll discuss, are absolutely critical.
Okay. And what about protecting the meaning and correctness of the data itself, even outside of active transactions?
Right, that falls under data integrity. This is about enforcing the semantic correctness of the data according to the rules you've defined.
Like what kind of rules?
The most common is referential integrity, usually enforced using foreign keys. If you have an orders table that references a customer ID in the customers table, a foreign key constraint ensures you can't create an order for a customer who doesn't actually exist in the customers table.
Okay. Prevents orphaned records.
Exactly. It also includes things like validation rules, ensuring a product price is never negative, or an email address follows a certain format and triggers, which are little bits of code that automatically run when certain data changes occur, perhaps to maintain an audit log or enforce complex business logic.
All right. So we have transactions, ACID, concurrency control, and data integrity. What's the final piece of the puzzle for these core responsibilities?
Security, of course. Access control. You need to control who can do what to the data.
Makes sense.
This involves 3 key parts. Authentication, verifying a user's identity, like username and password. Authorization, checking what permissions that verified user has. Can Jane read the salary table? Can Bob only update his own profile, not others? And auditing, keeping a secure log of who accessed or modified what data and when. This is crucial for compliance, like GDPR or APA, and for investigating security incidents.
Right. Without strong access control, all those other guarantees, integrity, consistency, could be undermined by unauthorized changes.
Precisely. It's the outer layer that protects everything else.
Okay, so we've mentioned COD and the relational model. The real beauty of it, the reason it was so powerful and enduring, is its strong mathematical foundation. It's not just arbitrary tables. It's based on set theory and predicate logic.
Right. It's formal. So data is represented as, what are the terms again?
Data is structured as relations, which you can basically think of as tables. These relations are composed of tuples, which are the rows or records, and each tuple has named attributes, which are the columns.
Relations, tuples, attributes. Got it. Sounds a bit abstract, though. How does this formality help?
That formal structure allows for very rigorous manipulation and reasoning about the data. The core concepts that give it teeth are keys and functional dependencies.
Okay, functional dependencies. You mentioned them briefly. Let's unpack that. X implies Y.
Right. We write it as $, right arrow, YLO. It means that the value or set of values in attribute set X uniquely determines the value of attribute set Y within any given tuple of that relation. So like in a table of employees, the employee ID would determine the employee name.
Exactly. Employee ID, right arrow employee name. If you know the ID, you know the name. There's only one name associated with that ID. It can also be sets of attributes like order ID, product ID, right arrow, quantity.
Okay. And why are these dependencies so important?
They are the absolute rulebook for the structure of your data. They define the integrity constraints, and more importantly, they are the mathematical basis for the process of normalization.
Ah, normalization. The
Yeah.
thing database designers are always talking about. Before we get to that, you also mentioned relational algebra. That's sort of the internal language.
Yes, think of relational algebra as the set of fundamental operations the database engine uses under the hood. When you write an SQL query, the database first translates it into an equivalent plan using these algebraic operators.
What are the main operators?
The core ones are selection, which filters rows based on some condition, think the where clause in SQL. Then there's projection, which picks out specific columns like the select list in SQL. And the most famous and often most complex is the join, which combines related tuples from two different relations based on common attribute values.
Okay. And understanding these helps understand how queries get optimized.
Absolutely. The query optimizer's main job is essentially finding the most efficient sequence and implementation of these relational algebra operations to satisfy your SQL query. Should it do the selection first to reduce the number of rows, then the join. Or join first, that's the optimizer's challenge.
Right. So, okay, let's tackle normalization now. This is the process everyone learns about for designing relational databases. Why do we do it? What's the goal?
The primary goal of normalization is to eliminate two major problems: data redundancy and update anomalies.
Redundancy is just storing the same information multiple times, right?
Exactly. Imagine a table where you store employee information, including their department name and department manager. If you have 50 employees in the same department, you're storing that department name and manager's name 50 times.
Waste space, obviously.
Waste space, yes, but worse, it leads to update anomalies. What happens if the department gets a new manager? You now have to find and update all 50 rows for that department. If you miss one, or make a typo in one.
Your database is now inconsistent. Some records show the old manager, some show the new one.
Precisely. That's an update anomaly. There are also insertion and deletion anomalies. Normalization is a systematic process of decomposing your tables into smaller, well-structured relations to prevent these kinds of problems.
So it's about achieving a kind of data purity. Let's walk through the key levels, the normal forms. What's the first one?
First normal form, 1NF. This is pretty much the mandatory starting point for any relational table. It simply requires that every attribute value must be atomic.
Atomic.
Meaning it can't be broken down further in the context of the model. More practically, it means no repeating groups or multi-valued columns. You can't have a phone numbers column that contains a list of numbers. Each phone number should ideally be in a separate row or a separate related table.
Okay, makes sense. Get rid of lists within cells. What's next? Often people aim for 3NF.
Yes, third normal form, 3NF, is often considered the standard target for transactional systems, OLTP. To get to 3NF, you first need to be in 2NF, which deals with partial dependencies on composite keys. But the key step for 3NF is eliminating transitive dependencies.
Transitive dependency. Okay, what's that?
A transitive dependency occurs when a non-key attribute depends on another non-key attribute, which in turn depends on the primary key. Remember our employee example with department name and department manager. Let's say employee A is the key. We likely have employee ID, right arrow department A, and department ID by our department name. That means department name transitively depends on employee ID via department ID. 3NF says this isn't allowed. You should factor out the dependency department ID, right arrow department name, into a separate departments table.
Ah, okay, so you have an employees table and a departments table linked by department ID.
Exactly. That eliminates the redundancy and the update anomalies related to department information within the employees table.
Okay. Is there anything beyond 3NF? You hear about BCNF sometimes.
Yes, Boyce Cod normal form, BCNF. This is considered a stricter version of 3NF and often the theoretical ideal. The rule for BCNF is simple but powerful. For every functional dependency, $6 right arrow violation to line that holds in the relation, X must be a superkey.
A superkey being.
Any set of attributes that uniquely identifies a row. A primary key is a minimal superkey. BCNF essentially says that the only things determining other attributes should be keys. It closes certain loopholes left by 3NF, especially in tables with multiple overlapping candidate keys.
So, if BCNF is the theoretical ideal, this perfect state of normalization, why don't we just always aim for BCNF in every database design? What's the catch?
The catch is performance, usually. Achieving BCNF, or even 3NF sometimes, often requires breaking tables down into many smaller
Right,
tables.
more decomposition.
And every time you decompose, you often need to perform more join operations later to bring that data back together when you query it. Joins, especially across very large tables, can be computationally expensive. They require a lot of I/O and CPU.
So there's a trade-off.
A very common one. In the real world, particularly in systems designed for analytics or reporting data warehouses, designers often intentionally denormalize the database schema.
Denormalize, meaning they consciously break the normalization rules.
Yes, they might combine tables back together or add redundant columns, accepting controlled redundancies specifically to reduce the number of expensive join operations needed for common analytical queries. They treat data purity and avoiding anomalies for faster query performance. It's a classic engineering trade-off.
Makes sense. Purity versus speed. Okay, let's quickly touch on SQL semantics again. We know it's declarative, you say what you want, not how to get it. But understanding the logical processing order is still important, right?
Absolutely critical for writing correct and efficient queries. Even though you might write the clauses in your SQL statement in a certain order, select first, then from, then where, the database engine evaluates them in a different fixed logical sequence.
And that sequence is...
Generally, it goes like this. 1, from and joins, determines the working set of tables. 2, where, filters individual rows based on conditions before any grouping happens. 3, group by Y, aggregates rows into summary groups. 4, having, filters those groups based on conditions applied after aggregation. 5, select, determines the final output columns, calculates expressions, applies aliases. 6, order by, sorts the final result set just before returning it.
Okay, so knowing the order matters. For example, you can't use an alias defined in the select list inside the where clause.
Exactly. Because the where clause is logically processed before the select list, where the alias is defined. Understanding this flow prevents a lot of common SQL errors and helps you think about how the data is being transformed step by step.
And modern SQL isn't just simple select from where anymore, is it? It's gotten much more powerful.
Oh, vastly more powerful. Features like window functions are a game changer for analytics. They let you perform calculations across a set of table rows that are somehow related to the current row, running totals, rankings, moving averages, without collapsing the rows like group by Y does.
Okay.
And common table expressions, CTEs, using the with clause, make complex queries much more readable by breaking them into logical named steps. They even allow for recursive queries like processing organizational hierarchies or bills of materials. Plus, most modern SQL dialects now have good support for handling semi-structured data like JSON or XML directly within the database.
So SQL is definitely not standing still. It's evolving to handle these more complex modern data needs.
Absolutely. It remains incredibly relevant and powerful.
All right, let's move down a level now into the engine room. How does the database actually manage the data physically? The first thing to grasp is the memory hierarchy.
Meaning the different types of storage and their speeds.
Exactly. You've got CPU caches, which are incredibly fast but tiny. Then main memory, RAM, which is fast nanosecond access times but volatile, meaning it loses data when the power goes off.
Okay.
Then you have persistent storage. Solid-state drives, SSDs, offer microsecond access times much slower than RAM, but way faster than traditional hard disk drives, HDDs, which operate in milliseconds due to their spinning platters and moving read-write heads.
So we're talking orders of magnitude difference in speed. Nanoseconds in RAM, milliseconds on disk. That's like 1,000,000 times slower.
It's a huge gap, and that performance chasm dictates so much of database architecture. The number one goal is to minimize accessing the slow, persistent storage, the disk I/O.
And how does the system do that? How does it hide that disk slowness? The primary mechanism is the buffer pool, or buffer cache. This is a large area of main memory, RAM, that the database reserves specifically to cache copies of data pages recently read from disk.
So it tries to keep frequently used data in fast RAM.
Precisely. When the database needs to read some data, it first checks the buffer pool. If the page is already there, a buffer hit, fantastic. It avoids a slow disk read. If it's not there, a buffer miss, it has to fetch the page from disk, bring it into the buffer pool, potentially evicting another page, and then satisfy the request.
Okay, so managing what stays in the buffer pool is critical. How does it decide which pages to kick out when it needs space?
That's governed by caching policies or replacement algorithms. Right. The most classic one is LRU, least recently used, kick out the page that hasn't been accessed for the longest time. Variations like the clock algorithm try to approximate LRU with less overhead. The goal is always to keep the pages most likely to be needed again soon in memory.
But wait, if you modify data in the buffer pool in RAM, how does that change get saved permanently, especially with that durability requirement from ACID?
Excellent question. This brings us back to the write-ahead logging WhatNeil protocol. It's the absolute cornerstone of durability and works hand in glove with the buffer pool.
Okay, remind us of the wall rule again.
The fundamental rule of WAL is, before a modified data page, a dirty page, in the buffer pool is allowed to be written back to its original location on disk, the log records describing that modification must first be written to a separate sequential log file on stable storage.
So the description of the change hits the disk before the change itself hits the main data file.
Exactly. Think of the log as the database's journal. It records every change sequentially. If the system crashes after the log record is safely on disk but before the dirty data page was written, it doesn't matter. When the system restarts, it reads the log, sees the record for the committed change, and can replay it to ensure the data page is correctly updated. This is the redo part of recovery.
And if the crash happens before the log record is written?
Then the transaction is considered not committed, and any partial changes it might have made in memory are irrelevant or will be undone, the undo part of recovery. The log is the source of truth for recovery.
Got it. Log first, then data page write. That's the key synchronization.
Yeah.
Okay, so data is safely stored and durable. Now, how do we find a specific piece of data quickly within potentially terabytes of storage? We can't scan everything.
Right, that's where indexing comes in. And the absolute workhorse, the most common and versatile index structure by far, is the B+ tree.
B+ tree. Why is it so dominant? What makes it special?
B+ trees are beautifully engineered specifically for balancing search speed with the realities of block-based disk I/O. They have several key properties. One, they're balanced. The tree automatically reorganizes itself on inserts and deletes to ensure the path from the root to any leaf node is always the same height. This guarantees logarithmic search time, the lookup n, where n is the number of items, and f is the fan-out, number of children per node. Performance degrades gracefully as data grows. 2. High fan-out. Internal nodes just store keys and pointers to child nodes, not the full data records. This means each node can hold many keys, making the tree wide and shallow, minimizing the number of node reads, disk accesses, needed to find something. 3. Sequential leaf nodes. Unlike regular B trees in a B+ tree, all the actual data pointers, or sometimes the data itself, reside only in the leaf nodes. Critically, these leaf nodes are linked together sequentially, like a doubly linked list.
And why is that linked leaf structure so important?
It makes range scans incredibly efficient. If you need to find all records between, say, date X and date Y, the B+ tree lets you search for the starting key, X, find its leaf node, and then simply traverse across the linked list of leaf nodes until you pass Y. You don't have to keep going up and down the tree. You just read the relevant leaf blocks sequentially off disk. Super important for many queries.
Okay, B+ tree is the default. But there are other index types for specific situations, right?
Absolutely. If you only ever need to look up records based on an exact key value, e.g. find user by user ID, and never do range queries on that key, a hash index can sometimes be faster. It computes a hash function on the key to directly calculate the location, giving you average $O lookup. But no ordering means no range support, and performance can degrade badly with hash collisions.
What about columns with very few distinct values, like a gender or status column?
For those low cardinality columns, especially in analytical systems, bitmap indexes can be extremely efficient. Instead of storing pointers, they use a bitmap, a sequence of bits, for each distinct value. If the value is active, the bitmap might have a 1 for every row that is active and a 0 otherwise. These bitmaps can be compressed very well and allow the database to perform complex logical operations, AND or NST, very quickly by doing bitwise operations on the bitmaps.
Interesting. And for geographical data, maps, locations?
For spatial data, you need specialized indexes that understand multidimensional space. The most common are arctrees, or variants like arctrees. They work by grouping nearby objects into nested bounding boxes. Searching for points within a certain geographic area becomes efficient because the index can quickly prune entire branches of the tree whose bounding boxes don't intersect the query area.
Okay, index types match to data types and query patterns. Now let's talk about a fundamental shift in how data is stored, column-oriented storage. Why move away from storing data row by row?
This was a massive innovation driven largely by the needs of data warehousing and analytics, OLAP. Traditional databases are row stores. All the values for a single row, like name, address, city, zip for customer 1, are stored contiguously on disk. This is great for transactional workloads, OLTP, where you're often inserting, updating, or deleting entire rows.
Right, you grab the whole record easily.
But think about a typical analytical query. You might want to calculate the average sales amount for all customers in California. In a row store, to get the sales amount and state columns, the database has to read the entire row for every customer, including columns like name and address that it doesn't even need for this query. That's a huge amount of wasted I/O.
Ah, okay, so a column store.
A column store, or columnar database, flips this completely. It stores all the values for a single column together contiguously on disk. So all the sales amounts are together, all the states are together, all the zips are together.
And how does that help that analytical query?
Two massive advantages. One, I/O efficiency. For the query average sales amount for customers in California, the column store only needs to read the sales amount column data and the state column data. It completely ignores the blocks containing name, address, etc. This drastically reduces the amount of data read from disk, often by 10x or even 100x. 2. Compression efficiency. Values within a single column are often very similar or repetitive. Think of the state column again, lots of CA, NY, etc. This homogeneity makes columnar data highly compressible using techniques like run-length encoding or dictionary encoding. Better compression means less storage space and even faster I/O because you're reading fewer compressed blocks.
Wow. Okay, so column stores are a huge win for analytics. Does it have downsides?
The trade-off is that point lookups or updates to individual rows can be slower. If you want to retrieve all columns for customer 1, the database has to stitch together values from many different column files, which can be less efficient than reading a single contiguous row. That's why you often see row stores used for OLTP and column stores for OLLP.
Got it. Okay, we have storage, we have indexes. How does the database put it all together? When I submit my SQL query, how does it decide whether to use an index, which join method to use, how to order operations? That sounds like the job of the query optimizer.
That is exactly the job of the query optimizer. It's arguably the most complex and critical component of a modern RDBMS. It takes your declarative SQL query, the what, and translates it into an efficient imperative execution plan, the how.
What are the main steps it goes through?
It's typically a multi-phase process. 1, parsing, checks the SQL syntax is correct and builds an internal representation, like a parse tree. 2, semantic analysis. Validates the query against the database schema. Do the tables and columns exist? Do the data types match? Does the user have permissions? 3, logical optimization. This is where the optimizer rewrites the query structure using rules based on relational algebra equivalences without considering specific physical details yet. It might push predicates down, apply where clauses earlier, eliminate redundant joins, or rearrange the order of operations based on logical rules. 4, physical planning, cost-based optimization. This is the real heart of it. The optimizer generates multiple potential physical execution plans. For each plan, it considers different access paths. In example, use B+ tree index scan versus full table scan, different join algorithms, for example, hash join versus sort merge join versus nested loop join, and different data flow strategies.
And how does it choose which plan is best? It can't actually run them all.
No, it definitely can. It uses cost-based optimization. The optimizer estimates the cost, usually a combination of expected I/O and CPU usage, for each potential plan. To do this, it relies heavily on statistics that the database maintains about the data.
Statistics, like what kind of information?
Things like the number of rows in each table, the number of distinct values in each column, cardinality, the distribution of values, often stored as histograms, the number of null values, etc.
Okay, and it uses these stats to guess how much work each step will do.
Exactly. It uses the statistics to estimate the selectivity of predicates. For example, where state equals CA, what fraction of rows will this match? And the cardinality, how many rows will likely result from this operation. These estimates flow through the plan. If it estimates that a where clause will filter 99% of the rows, it knows that doing that filter before a join might be much cheaper.
But what if those statistics are wrong or out of date?
That's the Achilles heel. If the statistics are inaccurate, the optimizer's cost estimates will be wrong. It might drastically underestimate the size of an intermediate result set early in the plan.
And that error?
That error compounds exponentially as it flows through subsequent joins or sorting operations. A small estimation error early on can lead to the optimizer choosing a disastrously bad plan, turning a query that should take milliseconds into one that runs for minutes or even hours.
Ouch. So keeping statistics accurate is a big deal for database administrators.
A huge operational challenge, and it's why there's so much research now into using more advanced techniques, even machine learning, to improve cardinality estimation and plan selection, trying to make the optimizer smarter and less reliant on potentially stale stats.
Okay, let's circle back to that crucial IM innacity, isolation. We need ways to manage concurrent transactions so they don't interfere with each other. What are the main mechanisms?
We talked about the goal making concurrent transactions appear serial. How is that achieved? The classic approach involves locking, right?
Yes, the traditional bedrock is two-phase locking, 2PL. It's conceptually simple, but effective at ensuring serializability.
Two phases. What are they? One, the growing phase. The transaction acquires all the locks it needs. Shared locks for reading, exclusive locks for writing. It can acquire locks but cannot release any. Two, the shrinking phase. Once the transaction releases its first lock, it enters the shrinking phase. Now it can only release locks. It cannot acquire any new ones.
Okay, and why does this guarantee isolation?
Because by holding necessary locks until it's done needing them, especially in the common variant called strict 2PL, which holds all write locks until the transaction commits or aborts, it prevents other transactions from accessing data in conflicting ways while it's in progress.
But it sounds like it could cause a lot of waiting. If transaction A holds a write lock on a row, transaction B has to wait to read or write that row.
Exactly. That's the major drawback of locking. Contention and reduced concurrency, especially for read operations. And worse, it's susceptible to deadlocks.
The deadly embrace. Transaction A is waiting for a lock held by B, and transaction B is waiting for a lock held by A. Neither can proceed.
Right. Deadlock detection and resolution mechanisms are necessary, which adds overhead. This performance limitation, especially for read-heavy workloads, is what drove the adoption of the modern alternative.
Which is multi-version concurrency control, MVCC, used by systems like PostgreSQL, Oracle, SQL Server now too.
Correct. MVCC takes a fundamentally different approach. Instead of having writers block readers by locking data, it allows multiple versions of a data row to exist simultaneously.
How does that work?
When a transaction starts, it gets a unique identifier or timestamp. When it needs to read data, the database shows it the version of the row that was committed and valid at the time the transaction started, or according to its snapshot isolation level. If another transaction updates that row concurrently, it doesn't overwrite the old version, it creates a new version with a later timestamp.
So readers don't block writers and writers don't block readers.
Generally, yes. Readers access a consistent snapshot of the past without needing locks, dramatically improving read concurrency. Writers might still block other writers on the same row, but the big win is non-blocking reads. The database eventually needs to clean up old, unneeded row versions, vacuuming, but the concurrency benefits are huge.
Okay, that makes sense. There's another approach mentioned sometimes too, optimistic concurrency control.
Right. Optimistic concurrency control, OCC, is kind of the ask for forgiveness, not permission approach. Transactions don't take locks while they're running. They read data, do their work, and keep track of the data they read, their read set, and wrote their write set.
Okay, so when do they check for conflicts?
Only at the very end during the commit phase. Before committing, the transaction enters a validation phase. It checks if any other concurrently committed transaction wrote to data that this transaction read. If there's a conflict, the transaction is aborted and typically has to be retried. If there's no conflict, it commits.
So it's good if conflicts are rare.
Exactly. OCC works best in workloads with low data contention, often read-heavy ones. If conflicts are frequent, the cost of aborting and retrying transactions becomes too high, and pessimistic locking like 2PL or MVCC is usually better.
Got it. Okay, we've covered isolation. Let's revisit durability and recovery. We know the wall is key. How does the system actually use that log to recover after a crash? You mentioned ARES.
Yes, ARES, Algorithm for Recovery and Isolation Exploiting Semantics, is the industry standard recovery protocol, or at least the principles are widely used. It leverages the wall meticulously to ensure we get back to a consistent state after a crash.
What are the main phases of ARES recovery?
On restart after a crash, ARES performs 3 phases. 1. Analysis phase. It scans the wall forward from the last successful checkpoint. It identifies which transactions were active, uncommitted. At the time of the crash, these will need to be undone. It also figures out which data pages in the buffer pool were dirty, had changes not yet written to disk. These might need changes redone. 2. Redo phase. Starting again from an earlier point in the log determined during analysis, it scans forward and reapplies the log changes for all transactions, committed or not. This ensures that all changes from committed transactions that might not have made it to disk are reapplied, bringing the database forward to the state it was in at the moment of the crash. 3. Undo phase. Now, it works backwards through the log, specifically undoing all the operations performed by those transactions identified as uncommitted during the analysis phase. This removes the effects of any incomplete work.
Wow. Okay, analysis, redo everything, then undo the incomplete stuff. That sounds robust, and checkpoints help speed this up.
Exactly. A checkpoint is a periodic operation where the database forces all dirty pages currently in the buffer pool to be written to disk, and then writes a special checkpoint record to the wall. This establishes a point in time before which recovery doesn't need to look for redo operations, significantly bounding the amount of log processing needed during restart.
Makes sense. Okay. Now for the really big leap, moving from one reliable database instance to distributed databases. Multiple machines, communicating over a network. Why go distributed?
The main drivers are scalability, handle more data and traffic than a single machine can, availability, system keeps working even if some nodes fail, and sometimes geographic distribution, place data closer to users.
But networks are unreliable, right?
Yeah,
They can be slow, messages get lost, parts of the network can fail.
precisely. That introduces the fundamental challenge, network partitions. What happens when one group of database nodes can't communicate with another group? And this is where the famous CCAP theorem comes into play.
Right, Brewer's theorem, the choose 2 out of 3 constraint. What are the 3 properties again?
The theorem states that in a distributed system facing a network partition, P, it is impossible to simultaneously guarantee both. Consistency, C, specifically strong consistency or linearizability. Every read receives the most recent write or an error. All nodes see the same data at the same time. Availability A. Every request received by a non-failing node in the system must result in a response, though not guaranteed to be the most recent data. The system keeps working.
So during a partition P, you're forced to make a trade-off between C and A.
Exactly, you have to choose. CP systems, consistency over availability. When a partition occurs, these systems will choose to maintain consistency. They might return errors or block requests to the partition nodes to avoid serving potentially stale or conflicting data. Think systems where correctness is paramount, like financial ledgers. Many traditional RDBMS clusters configured for strong consistency fall here, as do systems like HBase or MongoDB in its default config. AP systems, availability over consistency. When a partition occurs, these systems prioritize remaining available. They will continue to serve reads and writes, even if it means different nodes might temporarily have different versions of the data, leading to eventual consistency. Think systems where uptime is critical and temporary inconsistency is tolerable, like shopping carts or social media feeds. Cassandra and DynamoDB are classic examples.
Okay, so CAP forces a fundamental design choice in distributed systems. Now, if you do need strong consistency across nodes, especially for writes, how do you get multiple machines to agree on the outcome of a transaction? How do they reach consensus?
That requires a consensus protocol. The classic and often maligned protocol for distributed transactions is two-phase commit, 2PC.
Right. Phase 1, prepare. Phase 2, commit or abort.
Correct. A central coordinator asks all participating nodes if they are ready to commit, prepare phase. If all participants vote yes, the coordinator logs the decision and sends a commit message to all. If any participant votes no or times out, the coordinator sends an abort message.
Sounds reasonable. But you said maligned. What's the big flaw?
The critical flaw is that 2PC is blocking. If the coordinator crashes after the participants have voted yes and are waiting for the final commit abort, but before it sends the final decision,
Then the participants are stuck.
they are stuck in an in-doubt state. They don't know whether to commit or abort, and they must hold on to resources like locks, potentially indefinitely, until the coordinator recovers or an administrator intervenes. This can cripple availability.
Yikes. Okay, so what are the alternatives for achieving consensus without that blocking problem? We hear about Paxos and Raft.
Right. Protocols like Paxos and its easier-to-understand successor, Raft, are designed for achieving consensus on a replicated log rather than directly on transactions, though you can build transactions on top. They work differently, typically involving electing a leader node.
How does Raft work, roughly?
Raft simplifies consensus by focusing on leader election and log replication. One node is elected leader. All client requests go to the leader. The leader appends the command to its own log and replicates it to follower nodes. Once a command is replicated to a majority of nodes, the leader considers it committed and applies it to its state machine, eventually notifying the client. Raft has specific mechanisms to handle leader failures and ensure a log consistency designed explicitly for understandability.
Okay, so Raft provides a robust way for a group of nodes to agree on a sequence of operations. But then there's Google's Spanner, the system that claims global strong consistency. How did they seemingly defy CAP?
They didn't defy CIP, but they engineered a way around its harshest trade-offs by tackling the partition in a unique way, using time itself. Spanner provides external consistency, which is basically linearizability, across globally distributed data
So
centers.
magic.
Close.
Yeah.
Hardware magic, really. They developed the TrueTime API. Every Spanner server has access to highly synchronized time sources, GPS receivers, and atomic clocks. TrueTime doesn't return an exact time, but rather a time interval earliest, latest, that is guaranteed to contain the actual absolute time. The uncertainty, latest, earliest, is typically very small, just a few milliseconds.
Okay. They have really accurate bounded time. How does that help commit transactions consistently across the globe?
When a transaction is ready to commit, Spanner assigns it a commit timestamp based on TrueTime. Crucially, before releasing locks or making writes visible, it waits for a period equal to the maximum possible time uncertainty, that interval size. By explicitly waiting out the uncertainty window, Spanner can guarantee that any transaction assigned timestamp T actually commits after all transactions with timestamps less than T have completed globally. It enforces a strict ordering worldwide by leveraging synchronized clocks and waiting.
Wow. So they use precise time and controlled waiting to achieve linearizability, effectively minimizing the window where the C versus A trade-off bites during partitions.
Exactly. It's an incredible feat of engineering, turning a distributed systems problem partly into a physics and hardware problem.
Okay, so we saw how the limitations of traditional RDBMSs under web scale led to the rise of NoSQL. It wasn't really one thing, though, was it? It was more like an umbrella term for a bunch of different approaches.
Absolutely. The key realization was maybe one size doesn't fit all database needs. Different applications have different data structures, access patterns, and consistency requirements. So NoSQL led to this great diversification of specialized database types.
What were some of the main categories that emerged?
Well, probably the simplest were key value stores. Think of them like giant hash maps or dictionaries. You store a value, which could be anything text, JSON, and image, associated with a unique key, and you retrieve it using that key. Super fast for simple lookups.
Examples.
Amazon's Dynamo paper was hugely influential here, pioneering concepts like eventual consistency, decentralized design, zero master, and using vector clocks to detect conflicting versions when writes happen concurrently on different replicas. Redis is another massively popular one, typically run in memory for extreme speed, offering not just simple values but richer data structures like lists, sets, and hashes, making it great for caching, session stores, leaderboards, etc.
Okay, key value for speed and simplicity. What else?
Document stores became very popular, especially for applications where the data structure wasn't fixed or evolved rapidly. Systems like MongoDB and CouchDB, instead of rows and columns, they store data in flexible, hierarchical documents, often using JSON or a similar format.
And the advantage there is?
Flexibility. You can add new fields to some documents without having to formally alter the schema for all documents, which is a major pain point, schema migration, in traditional relational databases. Great for things like user profiles, product catalogs, content management where structure varies.
Right. And then there are databases specifically built for relationships.
Exactly. Graph databases like Neo4j. These are designed from the ground up to store and query data based on the connections between entities. Data is modeled as nodes or vertices representing entities and edges representing the relationships between them.
What kind of applications benefit most from graph databases?
Anything where the relationships are the primary focus. Social networks, friend connections, recommendation engines, who bought what, who liked what. Fraud detection, linking seemingly unrelated accounts or transactions, network diagrams, knowledge graphs. The key performance characteristic is often cited as over dollar or near constant time edge traversal. Following a relationship from one node to its neighbor is fast, regardless of the total number of nodes in the graph, which is something relational databases struggle with, requiring expensive recursive joins.
Okay, so NoSQL brought specialization, but then people started missing some things from the relational world.
They definitely did. They missed the strong consistency guarantees of ACID, the familiarity and power of SQL as a query language, and the maturity of the relational tooling. But they still needed the scalability and availability that NoSQL offered. This tension led to the NewSQL movement.
NewSQL. So trying to combine the best of both worlds.
That's the goal. New SQL systems aim to provide the horizontal scalability and fault tolerance typical of NoSQL systems, but without sacrificing ACD compliance and full SQL query capabilities.
How do they try to achieve that? Are there examples?
Several approaches. Some, like CockroachDB or TDB, are heavily inspired by Google's Spanner. They build distributed, strongly consistent transactional SQL databases from the ground up, using protocols like Raft for consensus and often employing MVCC. They aim for massive scale and multi-region deployments while still offering familiar SQL and ACD guarantees, often aiming for serializable isolation.
Okay, Spanner-inspired designs.
Right.
Any other new SQL approaches?
Another path is taken by systems like VaultDB. It achieves very high throughput by partitioning data across nodes and then executing transactions single-threaded within each partition, entirely in memory. If a transaction only touches data within a single partition, which is common in many workloads, it can run extremely fast without any locking or latching overhead, avoiding contention. Cross-partition transactions are more complex, but still possible.
Interesting. So optimizing for the common case of localized transactions. This whole trend seems to be about blurring lines. First, NoSQL moved away from relational, then NewSQL tried to bring them back together. What about the line between operational databases, OLTP, and analytical databases, OLAP?
That line is blurring too. That's the idea behind HTAP hybrid transactional analytical processing. For decades, the standard practice was to have separate systems. Your fast RDBMS for handling live transactions, and then a separate data warehouse, often columnar, for running complex analytical queries.
And data got moved between them using ETL.
Right. Slow, batch-oriented ETL, extract, transform, load processes, meaning your analytics were often hours or even days out of date. HTA aims to eliminate that separation and latency.
Can one system really be good at both high-throughput transactions and complex analytical queries?
It's challenging, but there are strategies. Some systems use dual-format storage. Maybe they store data primarily in a row format for fast transactions, but also maintain a columnar representation of the same data, or rest of it, for analytics. Others leverage MVCC snapshots. Heavily analytical queries can run against a recent, consistent snapshot of the data without interfering with ongoing transactions. The goal is to enable real-time or near real-time analytics directly on operational data.
Giving businesses much faster insights. Okay, let's shift gears again to even more advanced paradigms. Data isn't always static. Sometimes it's constantly flowing. What about stream processing?
Right. This is a huge area. Traditional databases work well for data at rest. Stream processing deals with data in motion, potentially infinite streams of events coming from sensors, applications, logs, click streams, etc. Systems like Apache Kafka, Apache Flink, and Apache Spark Streaming are designed to process these streams continuously.
What are the unique challenges in stream processing compared to batch processing?
Several big ones. First, how do you define computations on an infinite stream? You need windowing, defining finite chunks of the stream to operate on, like calculate the average temperature every 5 minutes, tumbling window, or calculate the average over the last hour, updated every minute, sliding window.
Okay, defining boundaries. What else?
Dealing with late data, what happens if an event from the 10.000/10.05 window arrives at 10.07? Do you ignore it? Do you recalculate the window? How do you handle out-of-order events? And then there's the challenge of state management. How do you maintain state, like running counts or sums, reliably across failures in a distributed streaming system?
And achieving correctness guarantees sounds tough too. You hear about exactly once, semantics. What does that mean in a streaming context?
Exactly. One semantics, EOS, is the holy grail of stream processing reliability. It means ensuring that, despite failures and retries, each incoming event is processed and affects the final result exactly one time, not 0 times data loss and not multiple times duplicates.
How is that even possible with potential failures?
It requires careful coordination between the streaming source, like Kafka, the processing engine, like Flink, and the output sink, like a database. It often involves techniques like distributed transactions or variations like two-phase commit, transactional writes to the sink, and idempotent operations in the processing logic designing updates so that applying them multiple times has the same effect as applying them once. For example, setting a value instead of incrementing it. It's complex but achievable.
Okay. Shifting to architecture again. Serverless and edge databases, these feel very cloud native.
They definitely are. Serverless databases like AWS Aurora Serverless or Google Cloud LODB Omni decouple storage and compute resources much more dynamically. Compute capacity can scale up or down automatically based on load, potentially even scaling down to zero when inactive, offering a true pay-per-use model. This simplifies management and can be very cost-effective for variable workloads.
And edge databases, what's the driver there?
Latency. Edge databases, like Cloudflare D1 or FaunaDB, aim to move the data and the compute physically closer to the end users, out at the network edge. By reducing the round-trip time, they can provide much faster responses for globally distributed applications.
But distributing data to the edge must bring back consistency challenges,
Okay.
like the CAP theorem again.
Absolutely. Edge databases often have to rely on weaker consistency models or specialized data structures to handle concurrent updates happening at different edge locations. One important concept here is conflict-free replicated data types, CRDTs.
CRDTs, what are those?
They are data structures designed such that concurrent updates made on different replicas can always be merged automatically without conflicts, guaranteeing eventual consistency. For example, a grow-only set, CLDT, only allows additions. If two edge locations independently add different items to the set, merging the sets simply involves taking the union, no conflict arises. Other CRDTs exist for counters, registers, etc. They enable optimistic replication and high availability at the edge.
Fascinating. And finally, the lines are blurring between databases and another huge field, machine learning.
Yes, this is a major trend. For a long time, you had to do complex ETL to extract data out of the database and move it into a separate ML platform for training and inference. This is slow and costly.
So now the ML is coming to the data.
Exactly. There's a strong push towards in-database machine learning. Many databases are adding capabilities to train and run ML models directly inside the database engine using SQL or specialized extensions. This avoids data movement, leverages the database's query processing power, and simplifies the overall workflow.
And looking even further ahead, there's research on using ML to build database components, like learned indexes.
Yes, this is still very experimental, but super interesting. The idea behind learned indexes is to replace traditional index structures like B+ trees with small trained machine learning models. The model learns the cumulative distribution function, CDF, of the key data. To find a key, you feed it into the model, which predicts the position or memory location of that key.
Whoa, a model instead of a tree.
Potentially. For certain data distributions, these learned indexes can be much smaller and potentially faster than B+ trees. However, there are still many challenges around updates, ensuring correctness. They often need a B-tree-like structure as a fallback, and generalization. But it shows how ML concepts are starting to permeate even the core internals of database systems. #tag 6. Security, privacy, and hardware frontiers. All right, we can't talk about databases without talking seriously about security and privacy. Controlling access is paramount.
We mentioned access control earlier. What are the main models used to enforce who can do what? SQL's grant revoke is one type.
Yes, the standard SQL model with grant and revoke commands implements discretionary access control, DAC. Discretionary means the owner of an object, like a table creator, has the discretion to grant permissions on that object to other users, and those users might be able to grant those permissions further.
Simple, but you said it was vulnerable.
It's vulnerable to the Trojan horse problem. If a user grants permission to someone who turns out to be malicious or whose account gets compromised, that malicious actor can potentially access or even pass on access to sensitive data in ways the original owner never intended. It's hard to track the flow of permissions.
So what's a more robust approach for larger organizations?
Most large enterprises rely heavily on role-based access control, RBAC. Instead of assigning permissions directly to individual users, you assign permissions to abstract roles like sales manager, accountant, read-only analyst. Then you assign users to one or more roles.
And the benefit is easier management.
Hugely easier. When someone joins the company or changes jobs, you just assign them the appropriate roles. When you need to change permissions for a job function, you update the role definition once, and it automatically applies to everyone in that role. It scales much better and reduces the risk of error.
Okay. Is there anything even stricter than RBAC?
Yes. For highly secure environments, like government or military systems, you often see mandatory access control, MAC. Here, access decisions aren't based on user identity or roles, but on security labels attached to both users, their clearance level, and data objects, their classification level. The system enforces fixed rules like no read-up, a user can't read data classified higher than their clearance, and no write-down. A user can't write data to a lower classification level. Access is mandatory, not at the discretion of owners.
Got it. DAC, RBAC, MAC, different models for different needs. Now, what about protecting the actual data bits themselves? Encryption.
Encryption is fundamental. A basic level is transparent data encryption, TDE. This encrypts the database files stored on disk. If someone physically steals the hard drive, the data is useless without the encryption key.
But transparent means the database decrypts it automatically when running.
Yes, TDE primarily protects data at rest. Once the database is running and authorized users connect, the data is typically decrypted in memory and accessible to the application. If you need finer-grained protection, say encrypting just specific sensitive columns like credit card numbers or social security numbers, even from database administrators, you need column-level encryption.
Okay, but there's this futuristic idea you hear about, computing on encrypted data. Homomorphic encryption.
Ah, yes, homomorphic encryption, HHE. It's often called the holy grail of secure computation. The idea is truly revolutionary. Perform computations like addition, multiplication, maybe even complex SQL queries directly on encrypted data without ever decrypting it.
So you could send your encrypted database to a cloud provider, they could run queries for you on the encrypted data and send back the encrypted result without them ever seeing your actual plain text data.
That is precisely the promise. It would fundamentally change cloud security and privacy.
Amazing. So why aren't we all using it right now? What's the catch?
The catch, unfortunately, is performance. Current homomorphic encryption schemes are incredibly computationally expensive. Running even simple operations on encrypted data can be thousands or even tens of thousands of times slower than running them on plain text data.
Oof. 10,000x slower. That's not practical for most databases today.
Not for high throughput operational systems, no. The overhead is just too massive right now. Research is advancing rapidly, bringing the overhead down, but it's still primarily a research topic or used in very niche, low-performance applications. It's not ready for prime-time database workloads yet.
Okay, so HE is the future goal. What about protecting user privacy and analytics today? When you query large data sets, how do you prevent revealing information about individuals?
That's where differential privacy DP comes in. It's a different approach, focused on statistical disclosure limitation. DP provides a formal mathematical definition of privacy.
How does it work? Does it encrypt the data?
No, it works by adding carefully calibrated random noise to the results of aggregate queries run on the raw data. The amount of noise is precisely calculated based on the sensitivity of the query, how much influence any single individual's data could have on the result, and a parameter called the privacy budget, epsilon.
So the query results are slightly inaccurate but protect individuals.
Exactly. The added noise masks the contribution of any single individual, making it mathematically improbable with a guarantee bounded by epsilon for an attacker to determine whether any particular person's data was included in the dataset by looking at the query results. You trade a small amount of accuracy for a strong, provable privacy guarantee. Each query consumes some of the privacy budget, limiting the total amount of information that can be leaked.
Interesting. A mathematical approach to privacy protection. Okay, let's shift from software and privacy to hardware. How is changing hardware influencing database design? You mentioned non-volatile memory, NVM, earlier.
Right. NVM technologies, like Intel's Optane persistent memory, are a potential game changer because they blur the line between fast, volatile RAM and slower, persistent storage. NVM offers speeds approaching DRAM but retains data even when the power is off.
So memory that doesn't forget, how does that impact databases?
It forces a fundamental rethink of durability mechanisms. If main memory is persistent, do we still need the traditional write-ahead log in the same way? Can we simplify buffer pool management? Can we directly manipulate persistent data structures in memory? It could potentially lead to much lower write latencies and simpler recovery protocols, though managing consistency across CPU caches and NVM introduces new complexities.
Okay, NVM blurring memory and storage. What about faster networks? You mentioned RDMA.
Yes, Remote Direct Memory Access, RDMA. This is a networking technology that allows one computer to directly access the main memory of another computer over the network with very low latency, crucially bypassing the remote machine's operating system and CPU.
Bypassing the CPU. How does that help databases?
It enables extremely high-speed, low-latency communication between database nodes. This is particularly important for disaggregated databases where Storage resources, holding the data, might be physically separate from the compute resources, running the queries. RDMA allows the compute nodes to access data from the storage nodes almost as if it were local memory, enabling independent scaling of compute and storage without the traditional network bottleneck.
Very cool. Okay, one final trend, tying a lot of this together, the rise of the autonomous database. What's the vision here?
The vision is essentially a self-driving, self-managing database system that requires minimal human intervention. Think of systems like Oracle Autonomous Database or similar initiatives from other vendors. The goal is to automate complex administrative tasks using AI and machine learning.
What kind of tasks can be automated?
Primarily three categories. One, self-tuning. The database automatically monitors its workload and performance, then adjusts configuration parameters, optimizes physical layout, creates or drops indexes, and tunes queries, all without a human DBA needing to intervene. Two, self-healing. The system uses predictive analytics to anticipate potential hardware or software failures and can automatically fail over, patch itself, or reroute workload to prevent outages before they impact service. Three, self-securing. Automatically applies security updates and patches, monitors for threats, encrypts data, manages access controls, and audits activity to protect against external attacks and internal vulnerabilities.
So the goal is to make databases more reliable, performant, and secure, while drastically reducing the operational burden on humans.
Exactly. Turning database administration from a reactive, often high-stress, manual job into a more strategic, automated oversight role. It's a major direction for the industry. Hashtag tag outro.
Wow. Okay, we have covered an absolutely enormous amount of ground here. We went all the way back to Codd's foundational theory in the 70s.
Through the nuts and bolts of B+ trees and right-ahead logging.
Faced the hard realities of distributed systems with the CAP theorem.
And then explored the incredible diversity of the modern landscape. NoSQL, NewSQL, HTAP, streaming, serverless.
It's really clear how far things have come. But what are the core principles that seem to endure through all this change?
I think a few key ideas remain constant. That need for data independence Codd identified separating the logical from the physical, the power of declarative queries like SQL, the non-negotiable requirement for transactional consistency, ACD or variations, and the perpetual quest for efficient data access through smart storage, indexing, and optimization. Those seem timeless.
And the big lesson from the last, say, 15 years seems to be that one size really doesn't fit all anymore.
Absolutely. The database landscape is mature, yes, but it's also incredibly diverse now. There's no single best database. There's only the best database for a specific job.
Which leads directly to this idea of polyglot persistence that you hear architects talk about.
Exactly. Modern applications often don't rely on a single database technology. They use a combination of specialized systems tailored to different needs within the application. You might use a rock-solid relational database like PostgreSQL for your core financial transactions.
Then maybe Redis for session caching to keep the website fast.
MongoDB for storing flexible user profiles or product catalog data.
And perhaps Neo4j if you need to analyze complex relationships for fraud detection or recommendations.
Precisely. The modern data architect needs to be fluent in multiple database paradigms and know how to choose and integrate the right tool for the right task.
Looking ahead, you briefly mentioned quantum databases. Is that science fiction or something we need to think about?
Well, it's definitely still deep in the research phase, very far from practical implementation. But the theory is fascinating. Quantum algorithms like Grover's algorithm offer a potential quadratic speedup for unstructured search, finding an item in an unsorted database in a nuller's time instead of the classical
Square root of n? That's a huge speedup for massive data sets.
Potentially, yes. Building stable, large-scale quantum computers is the huge hurdle, of course. But it shows that database innovation isn't stopping. It will likely continue to evolve fundamentally alongside breakthroughs in computing hardware, even exotic ones.
Okay, so maybe not quantum next year. But let's end with a final provocative thought for you, our listener, to chew on. If the technical scaling challenges handling more speed, more volume, more distribution are increasingly being solved by this diverse landscape of NewSQL, NoSQL, and specialized systems, what's the biggest data challenge facing large organizations today?
That's a great question. And I think increasingly the bottleneck isn't purely technical scaling anymore. It's organizational scaling and data governance. We're seeing the rise of concepts like the data mesh.
The data mesh, what's the core idea there?
It's a reaction against huge, centralized, monolithic data lakes or warehouses that often become bottlenecks managed by a central IT team. The data mesh proposes decentralization. It suggests treating data not as a byproduct stored in a central pool, but as a first-class product, owned and served by the specific business domain that understands it best.
So the sales domain owns the customer data product. The marketing domain owns the campaign performance product, not a central IT team.
Exactly. Each domain is responsible for the quality, usability, and discoverability of its data products. But to make this work without chaos, you need strong federated computational governance. That means defining standards, security policies, and interoperability rules centrally, but enforcing them automatically at the domain level, often through a shared platform.
Okay, so the provocative thought is, how does this organizational shift towards decentralization, towards data as a product managed by domains, fundamentally redefine the role of the traditional centralized database system, the DBA, and the whole data governance structure within large companies over the next decade?
Precisely. That's a question that requires thinking about business strategy, organizational design, and culture just as much as technology. And it might be the next big frontier in how we manage and leverage data effectively, something to definitely keep an eye on.
A fascinating place to leave it. Thanks for that incredible deep dive.
My pleasure. It's a deep topic, but hopefully that gives everyone a solid foundation.